Let's look at convergence of a sequence of vectors. Convergence is an important property which we require, especially in optimization problems. We need solutions to converge to a particular value, and to define convergence, we need the idea of norms. Okay, so look at convergence. So vector norms can be used. One of the most important applications of vector norms can be used to measure convergence of a vector sequence. Okay. What is a vector sequence? We have sequences generally defined by, we have vectors like x1, x2, etc. till xk. I think it's not most like 1, x2, etc. xk, where xk is the kth vector in this corresponding sequence. Similar to a sequence of real numbers, but instead of numbers, we have vectors here. Okay, let's formally define what a vector sequence. Convergence of the vector sequences. Let V be a vector space. Our field R or C. For the idea of convergence, we remember that we need to have an idea of norm as well. So let this function be a vector norm over defined norm V. We say the sequence x of a, where k is greater than or equal to 1, converges to vector x, which belongs to this vector space, with respect to the norm, the vector norm, if and only if the norm of xk minus x tends to 0 as k tends to infinity. This is written as limit k tends to infinity, norm of xk minus x is equal to 0 with respect to this norm. Or another way to write this is limit k tends to infinity, xk is equal to x. This is how we define convergence. So there are few important questions we have to ask in convergence. Question is, can a sequence converge in one norm but not in another? What is the relevance of it? So the choice of norm which we use here has a significance in the convergence. So suppose we take L2 norm and say the sequence converges, but we take some other norm, say L infinity norm. With respect to that norm, the sequence, will it converge or will it not converge? So there's a possibility that it will converge in one with respect to one norm and does not converge with respect to another. The answer is no if the vector space is finite dimensional. So in the course of this course, we've been dealing only with finite dimensional vector spaces. Okay, so in finite dimensional vector spaces, if a sequence converges to X with respect to one norm, then I mean, converge. No, let's not say it's exactly converging to X. It converges to some point in with respect to one norm, where even if you change the norm, the sequence will definitely converge. Whether it will converge to the same point or different points is another question, which we'll discuss shortly. Another question is, can a sequence converge to different points with respect to a given norm? So what we mean by this question is limit x tends to k tends to infinity, xk is equal to x with respect to a given norm, and limit k tends to infinity is equal to y with respect to the same norm and x not equal to y. Is it possible? Is it possible? The answer to this is also no. No. How can we prove this? So we're given that with respect to this norm, form of xk minus x tending to 0, and norm of xk minus y is also tending to 0, right? Let's take the norm of x minus y. If used a similar sort of trick to prove the lower bound of difference between norms as well. We will use a similar strategy here. This is equal to norm of x minus xk is xk minus y. You can write it like this. This triangle inequality. This is x minus xk plus xk minus y. In fact, xk minus x and x minus xk, in fact, are both same because we have the homogeneity principle. We can always take minus one outside. The value does not change. But we know that this is tending to 0 and this is tending to 0. This is less than or equal to 0, right? But by one, which is actually one property one of norms, which is non-negativity. Non-negativity. We know norm of x minus y is greater than or equal to 0. So this quantity is greater than or equal to 0 and less than or equal to 0 at the same time, which means that norm of x minus y is equal to 0. But since for norms, where this has to hold only if x minus y is equal to 0 or x is equal to y. So if a sequence convergence to one point with respect to a norm, then that point is unique. Okay. So those things are actually important. Now the next question is whether convergence with respect to one norm guarantee that it converges with respect to another norm. So does it converge to the same point with respect to multiple norms? Okay, we'll discuss this in the equivalence of norms in the next section.